aspects of jet transport operations is the rapidly varying environmental conditions. An airplane may take off in a warm, sunny location and land in cold weather conditions. This requires awareness and preparation. During this program, we will discuss cold weather awareness as it pertains to jet transport operations. We will develop this awareness by covering the effects of cold weather on airplane performance, ground maintenance, and flight operations. And we will conclude by posing some thought-provoking questions for consideration when preparing for cold weather operations. The recommendations made in this program are general in nature. Specific information is contained in the applicable maintenance manual, airplane flight manual, and operations manual for each Boeing airplane. One major awareness factor is the necessity of an aerodynamically clean airplane prior to flight. This is stipulated in U.S. Federal Aviation Regulations. After viewing this program, you will understand the importance of this requirement and realize why these airplanes are not ready for flight. For an airplane to fly, airflow over the wing surfaces produces an upward force called lift. A retarding force called drag is also produced. The amount of lift produced by a specific wing depends on the speed of the airflow over the wing. The faster the airflow, the more lift is created. This can be accomplished by either increasing the speed of the airplane, airspeed, or increasing the angle the wing makes to the airflow, angle of attack. During flight, both airspeed and angle of attack are varied to control and maintain the desired amount of lift. The airflow over the wing must be smooth and follow the shape of the wing to continue producing lift. If the angle of attack is increased too far, the airflow can no longer follow the entire shape of the wing. Lift is rapidly reduced, and the wing stalls. The airspeed at which this occurs is called the stall speed. The jet transport wing is designed primarily for high-speed flight. To fly at the low airspeeds required for takeoff and landing, the wing must often produce more lift than is available just from increasing the angle of attack. This is accomplished by adding high lift devices, such as leading-edge slats and trailing-edge flaps to the wing, which are extended for takeoff and landing. Operating regulations require that adequate safety margins must be maintained above the stall speed for takeoff and landing. These margins are included in the certified takeoff and landing speeds to allow for maneuvering, takeoff rotation, turns, landing flare, and gusty wind conditions and other safety factors. Certified performance speeds are determined using an airplane with smooth, clean surfaces. Surface contaminants such as ice, frost, and snow cause airflow disturbances which adversely affect the lifting capability of the wings. The horizontal and vertical tail surfaces are also affected. At the same time, the contaminants increase drag. The effect varies depending on the degree and location of the contamination. Ice can form in flight or on the ground. In flight, ice forms on the leading edge of exposed surfaces as the airplane flies through moisture at low temperatures. Airplane systems have been developed to prevent or remove this form of ice as necessary. On the ground, ice can form on exposed airplane surfaces from snow, freezing rain, or other similar weather conditions. This form of ice is extremely hazardous because it affects the airplane's ability to fly. The operational impact of contaminated surfaces is the increase in airplane stall speeds, thereby reducing or eliminating the required safety margins, and the reduced acceleration and climb capabilities caused by lift loss and additional drag. Therefore, it is necessary that all airplane surfaces are kept clean during cold weather operations. This is the intent of U.S. Federal Aviation Regulations. now look at the effects of cold weather on ground maintenance and the actions necessary to achieve and maintain a clean airplane. Ground crews preparing airplanes for flight must be aware of the unique requirements associated with cold weather operation, primarily those of anti-icing and de-icing the airplanes. Since climatic conditions may differ, the operator is expected to use procedures suitable for the current and forecast conditions at each airport. Chapter 12 of the Boeing Maintenance Manual offers guidelines for airplane anti-icing and de-icing. Anti-icing and de-icing refer to different maintenance actions. Anti-icing is the protection from ice, snow, or frost accumulation on airplane surfaces. This is accomplished by applying undiluted glycol-based anti-icing fluid to the clean surfaces. De-icing is the removal of ice, snow, or frost from airplane surfaces. This is usually accomplished by applying a heated mixture of glycol-based anti-icing fluid diluted with water to the contaminated surfaces. Two important factors determine how often fluids must be applied: weather conditions and fluid concentration. The degree of protection or holdover after application of anti-icing or de-icing fluid is therefore not accurately predictable. However, the more dilute the fluid, the shorter the protection time. The expected protection time should be established by the operator based on experience. However, one rule should be firm. Under precipitation conditions, de-ice as close to airplane departure time as possible. Equipment and materials vary from one location to another. If snow hasn't frozen to the surfaces, it can be brushed off. Ice, snow, or frost stuck to the surfaces can best be removed by a stream of de-icing fluid. Most locations have specialized equipment available to de-ice and anti-ice airplanes. For anti-icing or de-icing, commercial glycol-based anti-icing fluids which have been tested and proven compatible with airplane structures and finishes can be used. Now, let's see how anti-icing protects the airplane surfaces. Anti-icing fluid applied to a clean surface leaves a coating or film. The film has a lower freezing point than frozen precipitation, which now melts on contact with the airplane surface. As the film becomes diluted by melting precipitation, accumulation may begin. However, a residual film usually remains, inhibiting ice or snow from sticking and allowing for easy removal of any accumulation by subsequent de-icing. Removal or de-icing will be discussed next. De-icing requires a hot fluid applied to warm the airplane surface to break the ice bond. Ice, snow, or frost accumulations can then be flushed off. Note that unheated fluid is not effective for melting ice on the airplane. Fluid dilution guidelines for de-icing are provided in the Boeing Maintenance Manual, where recommended fluid concentrations for different ambient temperature conditions are shown. However, ice may form and adhere to the surfaces of an airplane, landing in precipitation with temperatures slightly above freezing. This can occur when the external surfaces of the airplane may be below the freezing point. This should be considered in addition to ground temperature when determining de-icing fluid concentration. When applying de-icing fluid below -2 degrees centigrade, heated de-icing fluid must be used. With the temperature between -2 and +1 degree centigrade, use either heated de-icing fluid or hot water. If hot water is used, it must be followed immediately by an application of anti-icing fluid. Above +1 degree centigrade, unheated water can be used for snow removal only. Unheated water can also be used for ice and snow removal in a heated hangar. However, anti-icing fluid should be applied before moving the airplane outside if the temperature is less than +1 degree centigrade. Let's look at some considerations that apply to airplane preparation during cold weather operations. In slushy conditions, check the airplane when it arrives at the ramp for slush accumulations and damage to surfaces, and de-ice when appropriate. Flush ice, snow, or frost from wing and tail surfaces from front to rear to avoid forcing liquid into hinge and drive mechanisms. Do not spray fluid directly at or into pitot inlets, static ports, TAT probes, engine and APU inlets, or other openings. If necessary, engines and APU may be operated while anti-icing or de-icing. However, the cabin air conditioning pack valves must be closed. Other precautions are also required. Wing surfaces must be clean. All control surfaces, including leading edge devices and slap gaps, must also be clean of ice, snow, or frost. Check hinges, tracks, and actuators for trapped moisture, ice, or snow, and de-ice as necessary. Wing flaps, slats, and spoilers should be retracted prior to snowfall or icing conditions to minimize the area of exposed surfaces. Tail surfaces must be clean, and the fuselage should be free of ice and snow to reduce unnecessary weight and drag. The radome should be free of snow to avoid reducing cockpit visibility during takeoff. The landing gear and door-moving parts should be de-iced. Gear sensors should also be cleaned of ice and snow, and then anti-iced. Additionally, the nose gear steering mechanism should be cleared of any ice. Do not attempt to move an airplane when the tires are frozen to the ground. Clear parking area of snow and ice. Probes, ports, and drains should be checked for obstructions within a 4-foot radius. Remove ice or snow from openings with a warm air source. Remove ice and snow from door and girt bar areas. Before closing the door, apply anti-icing fluid as needed to seals and latches. These and other cold weather maintenance guidelines are summarized in Chapter 12 of the Boeing maintenance manuals. Next, we will cover some topics concerning the effects of cold weather on flight operations. Icing may occur when the outside air temperature on the ground, or total air temperature in flight, is 10 degrees centigrade or below, and visible moisture in any form is present. Visible moisture can be in forms such as rain, snow, sleet, or ice crystals. Clouds are considered visible moisture, and so is fog when visibility is 1 mile or less. In addition, ice or snow, or standing water on the ramps, taxiways, and runways may cause engine icing during ground operations. Let's see what actions the flight crew can take to minimize the effects of cold weather. An exterior safety inspection should be performed. This inspection will ensure that all ice, snow, or frost has been removed from the airplane. The guidelines used for this inspection are similar to those used during maintenance. Review takeoff data to ensure all corrections have been made for existing conditions. For example, a slush-covered runway may require a change in allowable rate or B1 speed. Engine or nacelle anti-ice should be turned on after engine start. For all ground operations, when icing conditions exist or are anticipated. Taxi operations during adverse weather conditions require extra crew alertness. Let's discuss some of the areas that should be considered. Avoid lengthy ground operations in icing conditions. Shorten taxi time by remaining at the gate as long as possible. This reduces the time between de-icing and takeoff. When departing the gate, use a pushback instead of thrust reversers. The use of reverse thrust at any time may cause snow or slush to be blown onto the airplane or into the engines. Airplane surfaces must be re-inspected after using reverse thrust. Main maintain a greater distance than normal between airplanes when taxiing on ice, slush, or snow-covered areas. Snow or water blown up by another airplane's exhaust may freeze on contact with your airplane. This may be difficult to detect. In moderate to severe icing conditions, periodically run up the engines, as specified in the operations manual, to reduce the chance of ice buildup on engine probes. With low outside air temperatures, if the taxi route is through slush or standing water, taxi with flaps up. This reduces the possibility of water freezing on the flaps and restricting movement. A word of caution: do not accomplish the before takeoff checklist until flaps are extended. Before moving into takeoff position, make a final check to verify the airplane is still free of snow and ice. Never assume that snow will blow off the wings during the takeoff roll. If not completely certain the airplane is free of snow and ice, return to the gate. Prior to takeoff, make a static engine run-up. Check for normal engine indications and smooth operation. Takeoff from a snow or ice-covered runway should be made using normal procedures with a few slight modifications. Start the takeoff roll with smooth, even application of thrust. Differential thrust is normally not required for directional control. Use full-rated takeoff thrust. Reduced thrust takeoffs based on the assumed temperature method are prohibited. Monitor engine parameters for abnormal indications. For example, cross-checking EPR versus N1 can provide clues to erroneous indications caused by a blocked PT2 probe. Crosswind directional control during the initial takeoff roll may be reduced, particularly for light gross weight and aft CG conditions. Use caution not to oversteer the nose gear. Use rudder pedal steering for corrections to centerline. At VR, rotate the airplane smoothly at a normal rate, approximately 3 degrees per second. Be aware that a takeoff roll through snow or slush may contaminate the wing and tail surfaces, thereby reducing the airplane's safety margins. For the proper takeoff operating procedures in cold weather, refer to the appropriate operations manual. During flight, icing conditions should be anticipated. The anti-ice systems must be used as necessary to prevent or remove ice buildups. Do not operate the anti-ice systems when the total air temperature is above 10 degrees centigrade. If anti-ice is used during low thrust conditions, such as descent for landing, be sure to observe the minimum N1 limits. This ensures that sufficient bleed air is available for anti-ice. Landing on ice or snow-covered runways deserves special consideration. All available means of stopping the airplane should be employed. If available, arm the auto brake and auto spoiler systems before landing. Deploy the spoilers immediately after all main gear contact the runway. Lower the nose wheel and actuate symmetric reverse thrust. Do not hold the nose gear off the runway. The auto brake system will begin a smooth, symmetrical brake application. Without auto braking, as soon as the nose gear touches down, apply brakes smoothly with moderate to firm pedal pressure, and hold until a safe stop is assured. Do not pump the brakes. Let the anti-skid system do its work. Maintaining runway center line requires constant crew attention. A combination of reverse thrust, crosswinds, and slipper runways can cause the airplane to drift if it is allowed to weather vane. Be prepared to correct back to the runway center line by reducing reverse thrust and releasing brakes. Then, use rudder pedal steering and differential brakes to control direction. When back on the center line, reapply brakes and reverse thrust as required to stop the airplane. Finally, do not attempt to turn off the runway until speed is reduced to a safe level. Turns onto icy taxiways, combined with high taxi speeds, can cause skids. During taxi-in on snow or ice-covered surfaces, some similar ground operating procedures apply as when taxiing out. Use engine anti-ice and make periodic engine run-ups. In addition, move the stabilizer trim toward the full nose-down position in accordance with the operations manual. If the landing was made on a slush-covered runway, do not retract the flaps until they have been inspected for ice accumulation. Let's now look at information sources. There are two primary sources of cold weather information for flight operations personnel: the FAA-approved Airplane Flight Manual and the Operations Manual. These manuals should be referenced for specific guidance concerning cold weather operating procedures. The FAA-approved Airplane Flight Manual contains information on the certified limitations and use of anti-ice systems. The Operations Manual contains recommended operational procedures and specific performance data for each airplane. For example, it specifies corrections to apply to performance data when operating from slippery runways. Both maintenance and flight operations personnel must work together to ensure safe cold weather operations. Here are some questions for both to consider when preparing for cold weather operations. Which procedures will apply? Where can I look to find them? Are proper procedures being followed? Does the airplane require de-icing or anti-icing? Is the required equipment available to do the job now, or will a delay be necessary? How long will the ground protection last based on current and anticipated conditions? Are all required airplane systems working properly? Is the airplane free of snow or ice? Is it aerodynamically clean? To summarize, safe cold weather operation requires awareness from both maintenance and flight operations personnel. We've covered the importance of ensuring an aerodynamically clean airplane and discussed the critical role maintenance has in preparing an airplane for flight in a cold weather environment. Then we addressed the responsibilities that flight operations have in the safe conduct of flights in cold weather conditions. A review of the maintenance and operations publications and appropriate procedures ahead of time will minimize operating difficulties. Also, the quarterly Boeing Airliner magazine, distributed to all operators, highlights topics of current interest. For example, the October 1982 issue contains a detailed article on cold weather operations. The past record of safe cold weather operations occurred because proper procedures were followed. With your efforts, this will continue.